Yeah, so Gary Morrison, ARM in Austin, Texas, US of A. And yeah, although my background historically, or at least for the 15 years, past 15 years or so, has been with CPU verification and software modeling of CPUs. This past year I've been doing something a little bit different, well actually really different to be honest, and that's working with the OpenJDK JVM, and in particular I want to tell you folks, well first I want to thank Lenaro for giving me this opportunity to tell you folks about a study I did in the mid-year. I think it's like July, around there, anyway, of last year, 2018. It's about Java AOT. And I'm afraid I'm going to have to apologize in advance if we don't have much time for questions. If you can hold your questions in the end, to the end, I'd appreciate it. I got a lot of material here, so I'll try to leave you some time, but if not, you'll see that my email address is on the last slide. Feel free to send me email questions if we don't have time to go over them. So what is this Java AOT thing? Well, it's just fantastic. It's really an amazing, amazing new Java whole new compilation paradigm. It's just incredible. It lets you do it lets you do exactly what compilers have been doing for the past 70 years, frankly. Yeah, so this might be a little hard for us Java nerds to wrap our brains around, but you know, go with me here, right? Okay. It lets you compile your code down to native before you run it. And that's just, isn't that awesome? It's amazing. It's never been done before. Well, except for C code, of course, C++, Fortran, COBOL, Pascal, PL1. Actually, come to think of it, that's pretty much the way it's only been done. Okay. Okay, I'm being facetious there. And actually, that is an important point. Although the main point I'm getting to here is the comparison of the benefit that you get from AOT between x86 and AArch64. That's sort of the main thing I'm going through. I do want to also, sort of a secondary emphasis is where in particular in a Java framework this ahead of time compilation is a benefit for you. So that's sort of the secondary goal here. So let me, to motivate what exactly the Java AOT is all about. Can you guys see the screen from here? Let me step away a little bit. To motivate how AOT can be beneficial, let me first make sure we're all on the same plane when it comes to what you have without AOT. So before AOT got involved, most of you probably know that the Java C compiler does not compile down to the actual machine language. Well, normally, under OpenJDK it does not. It instead compiles down to a virtual machine language, which is, the language is called Java bytecode. And the machine that executes that, interprets that code, is referred to as the Java virtual machine, JVM. And so you use this Java C compiler to get a bytecode representation of your code, and then the Java virtual machine interprets that code. And interpreters are slow. So as you might imagine, the JVM has ways around that. It in particular has two JIT, just-in-time, JIT, JIT compilers that are very innovatively named C1 and C2. And the difference between the two is important. C1 compiles faster than C2, but the code is not as optimal. So C2 produces more optimal code than C1. Now, that's one of two ways that this mechanism, very important mechanism in the JVM called hotspot, works. You see, what hotspot does is it, method by method, figures out which methods require the most optimal compilations of the code. And in particular, it compiles them on 4 tiers, so it has a tiered compilation system, as they call it. The higher tiers, tier 4, is the more optimal, and it's for the code that runs the most. So if your code gets called a whole lot, it goes on to tier 4, the highest tier. And if it gets rarely called, it goes on to the lowest tier, tier 1. And if it almost never gets called, it'll just continue in the interpreter, and yeah, you could call that tier 0, some people do. But in any case, there are 2 ways, not just C1 and C2, again, C2 being used on the higher tiers, the more optimal tiers. There's another way in which it makes the code more optimal for the higher tiers, and that's what they call, in short, it's a profile-driven real-time optimization. So in the lower tiers, when it's running in the lower tiers, it will insert some instrumentation code to profile what your code does as it runs and what it, more importantly, does not do when it runs. So some various things, like for instance, null reference checks. If the pointers that you, not called pointers, but anyway, if the pointers that you put into those null reference checks are never, quote unquote never, null, then they will just simply strip out the code to check whether it's a null reference or not. And that's just one example, but there are all kinds of other really cool things, and it can do to code it can strip out and get some really extremely optimal code on tier 4. That process is referred to as warming up the code. Okay, so that's why they call it hotspot. It's the code that's its hottest as it discovers as it runs over in real time. It is the hot code will get the best compilation. And there's also a third compiler that's a new kid on the block, so to speak. It's called Graal, and Graal is very interesting, well, for various reasons, but in this regard, 2 reasons. First of all, it's written in Java, which is strangely Escher, in that first you have to use Graal, you have to first compile the compiler, which compiler then compiles your okay. Anyway, that's one thing. The second thing, more importantly, is that the ahead of time compilations are done using Graal. So to do those ahead of time compilations, they created an all new tool called JAOTC, Java Ahead of Time Compiler, JAOTC. And you can look up, I brought my very own pointer here. You can look up, Google anytime you like, JEP295. They'll tell you all the details of how AOT is supposed to work. Here's the big picture of 3 ways that I ran all the benchmarks in that I'm doing here. So on the left here is the normal way before any AOT got into the game. And as you can see, first thing you do is you write your Java code, and you run it through Java C, and it gives a class file which contains that Java bytecode that I was talking about. And then you pop it into the JVM, and hotspot does its thing, optimizing the pieces of code that are the most commonly run to the most optimal, and so forth. Now, if you want to get ahead of time compilation involved, then you take the class file that Java C generated and run it into this new utility called JAOTC, and it generates a .so file, runtime library. And there are 2 ways, as you can see on this picture, there are 2 different ways you can run JAOTC. One is with this command line switch called compile for tiered, and the other is without. If you do use the compile for tiered switch, then the .so that gets generated along with the original bytecode will go into the hotspot mechanism, and even though it can run native code right from the start, it can still optimize it even further using the hotspot mechanism. So you get the best of both worlds, so to speak, that way, right? Because it's running native code right out of the chute, but it can also become more and more optimal as it keeps going. If you do not run with compile for tiered, then it will not insert any code to instrument to get a profile the code that you're running, and it will not compile it any better. And what you see is what you get. You're not going to get any better performance as it runs further. So there's again 3 ways: just non-AOT, AOT tiered, and AOT untiered. And these tests, these benchmarks, I ran each of those 3 ways. And there are basically 2 suites, 2 test suites, or 2 benchmark suites that I ran on this. The first one, the first set, well, actually, I should warn you first that you're not going to see any real CPU names on here. I was asked to not divulge the names of the ARM partners whose CPUs I was running here, or their CPU names. So if you want the latest gossip on which ARM partner has the most optimal CPUs, my lips are sealed. Oh, but wow, there's great gossip here. No, but anyway, I'll just be calling them 1 and 2, and then the x86 core, I'll just call x86. But they're comparable. They're pretty comparable cores. They weren't like orders of magnitude difference. They were within a few tens of % in performance. Server market type of cores. And yeah, so the 2 sets of benchmarks, as I was starting to mention, the first set I referred to as the initial 5 benchmarks because they were the ones I ran first, and there are 5 of them. Wow, brilliant name, huh? So I call them on the slides I5B, the initial 5 benchmarks. I'll go over those first, but after that I'll go over the results that we got from SpecJVM. SpecJVM is, of course, an off-the-shelf test from the Spec Consortium test, and that's very different results. But I'll first go over the I5B, as I call them, the initial 5 benchmarks results. And it's important to understand on these how I ran them. So in particular, what I did is I took the basic workload that each of the tests do and put them into a big outer loop, right? And I ran that outer loop, timing the amount of time it took for each outer loop, each iteration of the test to run. And the important thing, of course, is that the hotspot is going to be optimizing code and re-optimizing code as each time you run it, it'll become more and more optimal. So that was the idea, to plot as the loop iteration time goes by, how much more optimal it became over time. So that's what they call warming up. And the point of AOT is to speed up the warm-up process because you're running AOT, you're running actual native code right from the start. That's the theory. Now, since it's a loop time, it's important to remember that these are lower is better kinds of numbers, right? Because they're execution times. They're not performance numbers, these are execution time numbers here. So lower numbers are better on these pictures here. I also need to emphasize that my goal in this process is to evaluate the efficiency of the AOT implementation. I'm not interested in, again, I'm not interested in gossip about who has the most powerful cores here. I'm interested in the relative efficiency of x86 versus AArch64 AOT implementations. So I had to, I had to do something to factor out, I suppose you could say, the different clock rates and differences in the efficiencies of the individual microarchitectures, like a bigger cache or whatever. So conceptually, I could have run, I don't know, Drystone or something like that on all of them and scaled the numbers appropriately. But I decided that a better benchmark would be that particular benchmark running non-AOT and then averaging not the first 10 but the second 9 loop iterations, and then use that as a scaling factor to scale everything against that. The first, since I was using the non-AOT code, that's mostly running in the interpreter, which is mostly pretty much identical code. So that way it was kind of a benchmark measuring itself in a sense. So in any case, remember lower numbers are better on these, and also I'm going to point out also that the y-axis here is a logarithmic scale. So first benchmark on the initial 5 is from our friends at Lenaro. Heard of them? And yeah, it's called binary trees, and I included it because it involves recursion, and recursive algorithms, of course, tend to have different, distinctive properties. I'll probably get out of the way so you can see. Distinctive properties, yeah, especially since they tend to affect the ease of doing inlining, right? Because it gets more complicated if you've got recursive algorithms. When to inline, when not to, becomes more complex. But in any case, so I included it for that reason. What are we looking at on this chart here? You're going to be seeing a few more like this. 4 more, in fact, since there are 5 benchmarks. This is the loop iteration number, as you can see, 500 total loop iterations. And this then is, as I mentioned, that relative logarithmic scale execution time of that particular loop iteration. So again, it's an execution time, so lower numbers are better, remember that. Now, I am only showing the AOT runs. I'm not showing the non-AOT runs in here because I've already got 6 lines on the chart, so I didn't want to make them too complicated. So I'm not including the non-AOT runs. These are strictly AOT runs. And what are the colors? Well, as you can see, orange and darker blue, if you can tell for the haze of the lights here, darker blue color there and orange, those are tiered for the orange x86 and untiered AOT on the blue, and then yellow and gray for the first of the 2 AArch64 cores, and then nice flat line there, look at that, for green and cyan for the second of the 2 AArch64 cores. Now, the first thing that was really interesting about this particular run is that tiered, compiled for tiered or not, didn't make a lot of difference on any of the cores. That was really curious. Now, you see, like for instance on the x86 picture, you can see that the orange and the blue are pretty much right on top of each other. That's kind of curious. What does that mean? Well, that means that the code that I AOT'd did not get recompiled for a higher performance by. So what is getting changed? Obviously, the performance changes a whole lot through the run. Well, for x86 at least, it does. Obviously, not for that second AArch64 core. It did not. Well, it's important to understand that although I AOT'd the entire benchmark itself, I could not AOT the entirety of java.base. And if you look at JEP 295, like the one I was talking about earlier, it describes a procedure for how to AOT the java.base, the runtime libraries and so forth. And some portions of that are just this require way too much memory. It's not feasible to AOT all of it. And indeed, I checked to make sure that yes, what's dropped when the performance went way up here on the x86, indeed it was a piece of java.base getting compiled and hotspot helping out there. And yeah, so the first thing that I get from this is that if you're going to hear me saying this a whole lot, okay? If I get a chance to look at this whole test, this whole process again in more detail, I would like to see this. And in particular, this case, I would like to understand in more detail why we were not able to get that reduction in performance there, whereas x86 was able to. Now, that's a hotspot thing, right? That's something that hotspot was able to do. That's not an AOT implementation issue. So, important point there. So I would want to understand why we were not able to do that, but x86 was. So, yeah, keep on moving. The second benchmark, this is one that I supplied the code for, and it doesn't really exercise anything much in particular. It's really just pretty much ho-hum, boring, average, run-of-the-mill Java code. It's a lot like array searches and things like that. It's the thing that I found most interesting here is the detail on this opening, just early area here. That's the essence of warm-up right there. As you can see, there's some very interesting little, you see x86 managed to drop down pretty quickly there. And whereas, especially the first of the two AArch64 cores, you can see that it stayed pretty high for, pretty slow, in other words, for a while, and then finally managed to drop down a bit. So what I would like to do, if I get a chance at some point to go over this in greater detail, I want to go over all of these steps that happen one by one and understand why x86 was able to optimize out more than we were. That's what I would like to be able to do sometime. This next one is another one that I supplied the code for, and to be honest, it's really not as much a benchmark as it is a test. Well, actually, it is a benchmark in the sense that if the test didn't pass, and it did, as you'll see, the test did pass. If it did not pass, then I would be able to get some numbers on by how much it failed to pass. But let me tell you what this was intended to deal with. There's this, okay, so if Hotspot optimizes out a chunk of code, they call that optimizing, obviously. It can later find out, whoops, the profile of the code changed, right? Okay, in which case it has to de-optimize, meaning that it has to hop back into the interpreter, or at least a less optimal compilation, and recalculate the statistics that it can use to optimize out chunks of code. And that's referred to as a de-optimization. And to do that, the performance is going to drop really significantly while it's regathering more new statistics about how the code runs. Now, in the case of AOT, you have the advantage that you don't have to drop back into the interpreter. You could drop back instead to the code that you compiled ahead of time, in which case we would expect that the performance upon de-optimization would not go down anywhere near as much as if it had to drop back into the interpreter. And I'm not showing, as before, I'm not showing the non-AOT runs here, but indeed, when you look at them, they really jump up. Every time it de-optimizes, they really jump up and sort of stair-step their way down from there. And so what I see here is some fairly flat lines. I would expect to see a de-optimization here, a de-optimization here, a de-optimization here, and what you see mostly are fairly flat lines. So that is my test, was that it does indeed not go back to the interpreter. It instead uses the AOT code that is higher performance, therefore, which means that it passed. Now, if it had not passed, if it did not go back into then I would want to see for how long, and therefore how much we could improve it, but thankfully it passed. Just a little more detail here. What the test is doing is it's creating a long array of superclass objects, okay, and then filling it with a run of subclass 1 objects, a run of subclass 2 objects, subclass 3, subclass 4, 1, 2, 3, 4 again. And then it's going through the array, running a polymorphic method, okay, that is implemented in each of the subclasses. So the point being that it's running a different implementation of that method in each of these segments of time. So the point being that it would start here and say, okay, what is this one? It's subclass 1, okay, run that method. Subclass 1, run that method. Subclass 1. I'm starting to see a pattern here. It's always subclass 1. So it writes the code to always invoke subclass 1. And then all of a sudden I yank the rug out from under it, so to speak, and change it over to subclass 2. And it says, whoa, hold on, and de-optimizes back to the AOT code and runs the second class method. And now what's going on with this big bump here on the subclass 4 is that the main difference between the 4 different subclasses implementations of that method is a floating point operation, floating point add, subtract, multiply, and then divide. And by golly, floating point divides are much slower than floating point adds, and so forth. Except for, look at this second AArch64 core. Apparently it has a dang good floating point divide there. Interesting. Anyway, okay, I'm babbling too much on this one. The fourth of the 5 initial 5 benchmarks, also compliments of Lenaro. Thank you again, Lenaro. And this one is mandelbrot set, you know, the fractal, yeah, right. I originally included it because it has a lot of floating point, so I wanted to get a reading on floating point, right, you know. Yeah, sure, but that turned out to be the least of the interesting things about it. The by far vastly more interesting thing about it is that there was this enormous chunk of code that Hotspot was able to chop out of it. And as you can see, it went down the performance went up by a factor of like, what, 3 orders of magnitude or something. It was down to like just a few, I think it was like 10, 12 clocks per loop iteration. It really chopped out a huge chunk of code. But what's really interesting here, again, if I get a chance to go over this in greater detail, I would like to understand why the AArch64 cores were able to optimize it out substantially sooner than the x86 cores. Because that's a good thing, right? I would want to see what we're doing right there and make sure that if we, you know, make changes to Hotspot that we don't negate that advantage. So I would want to understand in more detail what the decision process there is. And the last one of the initial 5 was also from Lenaro. And yeah, they call it regexdna, and as you might imagine, it does a lot of regular expression matches. And of course, I wanted to include that because regular expression matches are pretty common. And yeah, so DNA, because it's has these, I don't know if it made them up or whether the real actual DNA sequences, but it's grepping for AGTC, yeah, anyway, you see the idea. The thing, okay, so not terribly surprisingly, the untiered, there's nothing behind me I'm about to trip over and crash into or anything, right? Okay, the untiered AOT numbers were less optimal, not surprisingly, because it couldn't, you know, do real-time optimizations as you would expect, and the tiered AOT were better. So nothing really surprising there, but what was surprising was that I would have expected the tiered AOT to sort of putter along till maybe about here or so and then drop down. So apparently it was able to, tiered AOT was able to, the Hotspot was able to optimize stuff amazingly fast. So after like 10 iterations or so, boom, it immediately optimized this out. I would really want to understand how it was able to optimize it so fast. I think my hypothesis, if I were to study this further, is that we would find that there's some operation in there that it's doing, even in one single loop iteration, many times. So even though it only ran a few loop iterations before it dropped, it nevertheless was calling that function many times. Therefore, it got hot really quickly. That's my theory. That's my guess. I would want to verify that, though, if I do get a chance to pursue this further. So this is a quick summary slide of my what would be interesting to look at. So in short, definitely want to see what exactly is, you know, optimizing there on x86 that's not in AArch64. Get all the details of what's going on there, and not really much there. Not a lot to look at here. And again, the timing of that optimization I'd like to look into further. And then finally, why it would optimize so quickly. So a lot of those, notice, are not AOT related. A lot of them are just simply the Hotspot implementation, being able to optimize things differently. So those are things that would be interesting to explore further if we get a chance to look into this further at some point. Okay. Yeah, so the other set of benchmarks that I did, excuse me, dry mouth. SpecJVM, and as I mentioned earlier, it's off-the-shelf standard, you know, spec consortium, all kinds of famous spec, you know, spec CPUs, but yeah, anyway. This is one of them, and it's intended to be very real-world Java type functionality. Things like, XML parsing, various scientific things like FFTs or Monte Carlo analysis. Well, you get the idea. Very real-worldy kinds of things. I ran these on the same core types, well, not just the same core types, but in fact, actually the exact same machine, the same silicon. So the same machines, and also ran them under the same usage cases: non-AOT, AOT tiered, and AOT untiered, just like I saw on that slide with the flowchart earlier. Now, there are two ways you can run SpecJVM. The normal way, let me describe how such a test works. The normal way is it has a bunch of operations, as they call them. Operations are fairly small pieces of code, okay? And you can string these operations together into what they call iterations. And then the iterations you can keep running for any specified amount of time. You specify how long you want to run them. Now in my case, I ran them for a fairly short period of time. Why? Well, because between AOT tiered and just non-AOT, if I ran them for a long time, then the amount of time when it's running the AOT code would be a tiny percentage, and it really wouldn't make any difference. So I wanted to run the test for a fairly short period of time in order to be able to see any difference at all between AOT tiered and non-AOT. So I ran it for only 15 seconds on the normal way of running it. Now, the other way that you can run SpecJVM is especially interesting for AOT. And that's what they call startup tests. And these startup tests, what they do is they pull up an all-new, fresh JVM right from scratch, absolutely newborn. And they tell it to run one operation, tiny little piece of code. And then they measure the time, tear it down. And that's the number that you get out of a startup test. Now, that is where you would expect AOT to really shine, right? Because it's either going to run that tiny piece of code in native with AOT, or it's going to run it in the mostly in the interpreter, right? So that's where you'd expect to see the biggest difference. So I was very interested, especially in those startup tests, but of course, all of them for that matter. Now, what did I see? Not terribly surprisingly, untiered AOT cases were kind of slow, especially on the non-startup cases, in the normal running cases, because it couldn't take advantage of the real-time optimization. So that's not surprisingly slowed them down quite a bit. However, what was surprising is that even tiered AOT, which should be the best of both worlds, right? You know, you're running native code right out of the chute, and you'll be able to optimize it even further, right? In some of those cases, it was actually somewhat slower than non-AOT, which was interesting. In fact, it wasn't, mostly it was just a few percent, but sometimes it was more than just a few percent. So I was like, I have a theory. And we'll get to that. So, yeah, wanted to look into that. I can't possibly show you all of the output from SpecJVM. The whole point of SpecJVM is it generates just reams and reams and reams and reams of gorgeous data. It's really awesome stuff. Very useful. But I'm going to show you a few cases that illustrate these points in particular. And I need to warn you ahead of time what I showed you previously. Lower is better, not anymore. Higher numbers are better now, okay, because these are operations per second or millisecond or whatever they are. I can't remember off the top of my head. These are performance numbers. These are not execution time numbers like you were seeing previously. These are performance numbers, so high numbers are good, right? Also, they're not logarithmic anymore. Yeah, so I'm just going to point out a few cases. Again, I can't show you all the data, it's just enormous. This, as you're seeing, is this is a chart of the normal execution, not the startups. Well, actually, the startups are, it does summarize the startups across here, that line. But anyway, the normal runs for the second of the two AArch64 cores. The numbers for the others look kind of similar. Again, I can't show you everything, but this was pretty telling. The benchmark, obviously you can see the benchmark here. Any given benchmark is a row across here, as you can see. And there are actually various sub-benchmarks in each of those, and this is the average of all of them appropriately. Now, the first data column is the performance numbers. Again, high numbers are better. For non-AOT. Then here is untiered AOT. So again, we're not able to get the real-time performance optimizations because hotspot is turned off for the methods that IAOT, at least. It's still able, as I mentioned, Java-based, some of Java-based can still be optimized further. This then is how much the performance increased from non-AOT to untiered AOT, and the increase is negative, meaning that it went down. It went down by quite a lot, in fact, as you can see, like negative 62%. It went way down. So that's what you would expect, basically, right? You would expect that you don't get the real-time performance improvements, so it will lose performance when you go to non-AOT, excuse me, to non-untiered operation. However, this is the tiered AOT numbers, and look, a lot of them are negative as well. -3. Most of them are like, you know, within 10%, but look at these. These are the 10% or more. One of them's down by 14%. This one's up by 10%, so that's good. But the point being, these are pretty comparable numbers with non-AOT. And yet it's able to run, you know, native code right out of the chute. What's going on? I have a hypothesis. Okay, I don't know. But again, if I go over this in more detail, I will like to verify this hypothesis. I think what's going on is that it just simply takes, the problem is, the difference is not warm-up time, the difference is startup time. That it simply takes time to load the code from the .so file, and therefore you are getting penalized for the extra time. With AOT, you're getting penalized for the extra time to load the AOT code from the .so file. And I think that what we're finding is that it's pretty much canceling out all of the, or majority of the benefit that you get from running native code right from the start. I bet that's what it is, but I don't know that for sure. And if I do get a chance to go over these numbers in more detail, I would want to verify that hypothesis, but I think that's what it probably is. Now, let me zoom in specifically on the startup tests. Okay, so these again where they fire up a brand new JVM, fresh out of the cradle, and tell it to run one tiny little piece of code, which can't warm up very much, right? Hotspot can't warm it up very much because it's a tiny piece of code, and then tears it right down, measures that time. Now, in this case, the numbers, the loss, you can see there's not as much yellow here, right? The amount of loss in performance is not quite as huge. Again, because it's this, the non-AOT operation, you know, so it's hotspot is not able to improve the performance of the code as much because it's just a tiny little piece of code. So so again, you still get some hit here, and again, I think that's because, I bet that that's just simply because we're losing a lot of time just simply loading the code from the .so file, and that's compensating for a lot of the benefit that you get for running native code right out of the chute when it finally loads it. So that's what I think is going on. But again, I haven't been able to check that, and I'd like to be able to do that sometime if I get a chance. Let me zoom in on a couple of cases that I thought were especially interesting, and they're on these summary charts up here. But anyway, this one is one of the startup tests. It's a Monte Carlo analysis one, and again, this is, you know, startup test. Again, a little tiny piece of code that it fires up in an all fresh new JVM. Now, what I thought was kind of interesting here, notice between non-AOT and AOT tiered, so that's both using hotspot, but this one has the AOT'd, you know, native code that it can run right out of the chute. This does not. x86, that's what this medium blue, I guess you can call it, it's kind of hard to tell with the lights on, but anyway, is not a lot different between non-AOT and AOT tiered. But look at that. There's quite a bit of a drop there from non-AOT to AOT tiered on AArch64 cores. That's interesting. That might suggest that our ability, our speed of loading code from .so files may not be as good as we'd like it to be. That's a possible interpretation. Again, I'd like to understand that to be sure whether that's what's going on or what. But that would be very interesting to see. But otherwise, as you can see, very roughly proportional in the case of untiered AOT, roughly proportional. Here's another case that I thought was, looks like I'm making pretty good time, good. Another case that I thought was kind of interesting here. In this particular case, also a startup case, so again, this is a fairly small piece of code, so not much hotspot optimization going on here. Not a lot, some maybe, but not a lot. And in this particular case, as you can see, the non-AOT versus AOT tiered performance, you know, not wildly different, somewhat different. Again, I think you're getting a trade-off between the AOT, the benefit of AOT and the downside of having to load the code, I think. But they seem to be pretty well canceling each other out. However, look at this. On the untiered case of this same test, x86 did not drop all that much in performance compared to non-AOT or AOT tiered. x86 did not drop a whole lot, but both AArch64 cores did. I'd like to look into that, figure out why exactly this particular chunk of code, what is it about this particular chunk of code that makes an unusually large drop there. That's probably some hints about things that we could improve here. So that was a curious case. All right. I think we'll actually have some time for questions. Yay. Overall conclusions. You know, when I went into this, I was hoping to find a silver bullet, a way that AOT could be a silver bullet to reduce all of your your hotspot warm-up issues down to nothing. I was kind of hoping that you would never have to worry about warm-up ever again. And it really wasn't that simple, to be honest. It was not really okay, here's what I'm getting at. My question, what sort of code, conceptually speaking, what sort of code should benefit from AOT, right? It's got to be something that does not benefit from hotspot, because assuming that you're running AOT tiered, right, which is where you get the best of both worlds, right? Assuming that it's AOT tiered, what kind of code would benefit most from AOT? Well, it would be something, clearly it would be something that involves a whole lot of code that doesn't get hot. So it's a whole lot of code that hotspot never can warm up for you, right? That would have to be a whole bunch of code that only gets invoked once or twice or pretty rarely, right? But that's in the simplifying, basically that's straight line code is what it really comes down to, right? It's code that basically doesn't get invoked more than once, basically, or very rarely anyway. So it's basically straight line code. Are there any real world applications that involve a whole lot of straight line code? I don't know, maybe. I don't really know of any. If there are, I bet AOT would help you a whole lot, but I kind of doubt it, really, that there's a whole lot of straight line code applications, a lot of applications that involve a lot of methods that rarely get invoked, you know, get invoked very infrequently. So I'm kind of pessimistic, really, to be honest with you. I'm kind of pessimistic as to how much AOT really is going to help a real world application, frankly. One thing I do see very clearly now is that it's important to choose very carefully what methods that you do put into your AOT.so file, because as we noticed, or apparently saw, loading that .so file does take quite a bit of time. So you probably want to only put in the functions or the methods, that are the most beneficial, so that you don't burn a whole lot of time finding the particular ones that are critical and burning a lot of time loading that code. And so maybe you can get a better result by being picky about which ones you put into the .so file from AOT. But beyond that, to be honest, I'm really I'm not really all that optimistic about how much AOT can help, based upon what I've seen here anyway. Okay, yeah, so we might. Yeah, I think we still got a little bit of time. You're welcome to ask questions, and if not, if you want to, you're welcome to email me questions as well. So, yeah, let's see, what's the, what is it? Korkunkrop, as they say here in our host Thailand, except they say it right, except they pronounce it right. Korkunkrop, right? Okay. So much for embarrassing myself. Okay, yeah, questions?
I've got one.
Yeah.
So did I understand correctly, Gary, that the de-optimized actually performed better with AOT because it didn't go back to interpreted? Was that correct?
Yeah, that was really what I wanted to test with that.
So that would mean then for long-running workloads, when we get something that would traditionally cause a big spike, we've taken the edge off the spike. Mm-hmm. So that would be quite a good thing.
That could be, especially if you have real-time oriented code,
yeah.
It could be very beneficial. Mm-hmm. Yeah.
Yeah.
Now there's another way in which that I didn't mention, and one of my colleagues, James Young, did some study on this, and it's worth pointing out. There is an important way, regardless of what you're seeing here, there is another very good benefit to AOT, and in particular AOT untiered, is that you're not forking off nearly as many of these auxiliary, ancillary threads that are doing the compilation, extra compilation for you. So there's a less junk work going on in the background when you do that. So that is another, that's a definite benefit as well.
I've got the microphone.
Two questions. Could you reproduce your results on x86 as well that you've found on ARM64?
So part of the point here, of course, is to compare the benefits, how much benefit you get from AOT from x86 to AArch64. As you saw, there were some differences in how much benefit and how they benefited, and it wasn't entirely just AOT differences. In this case, it's a hotspot, difference here. But yeah, so there were cases where things would help on x86 more or less than on AArch64. I'm sorry, is that what you're asking? Or?
The second question, is there any memory,
benefit there?
Benefit when using AOT?
Okay, yeah, okay. That partly relates to a different but related topic, CDS. Yes, yes, there are benefits, but it's harder to quantify in the sense that, okay, so there is underlying the Java JVM, there is the code cache where when it does a compilation, it will compile the code into the code cache, and there is a certain amount of space that allocates for the code, for the code cache. And as you might imagine, if you're not swapping stuff in and out of the code cache, or more importantly, if you're able to keep things in the cache, then if you de-optimize, you're more likely to be able to pop back to an earlier, more optimal version of that particular method. So the result then is if you throw more memory at it, not surprising, you'll get better performance. Now, in the case of AOT, if indeed you can pre-populate, in essence, that code cache. I think it goes into a different cache, but in any case, if you can pre-populate that code cache with some very optimal code, then like we saw on the de-optimize picture here, you can go back to a more optimal version and not have to have as many spots in the code cache for these successively more optimal and versions of it, because you have one really good optimal version that you can pop back to. So potentially yes, but it's an involved topic, and I can't claim to I can't claim to answer that in a general way, I guess is a better way to phrase that. But yes, there are memory footprint benefits of effects upon it.
One other possibility would be that the AOT compiler is doing a much better job on optimizing the x86 code than it might just be a more mature compiler than the obviously you need an expert in both to go and look at the code to find that out.
Yeah, so first of all, and I'm glad you mentioned that, because a very important point here is that this is the Graal implementation from, again, mid-late last year. And Zheng here, he runs a team in Shanghai, very smart team in Shanghai, who has been doing some very valuable improvements to the Graal implementation recently. So if I had time, I don't, believe me, this took a lot of time to run. If I had time to rerun all this stuff now, we might get some significantly different results, because Zheng's team has been doing a lot of good work since then. So yes, I'm glad you mentioned that. Yes, sir.
So it's been a while since I've used Java, but one of the early promises was that you could compile it once and run anywhere. When you run your tests, do you have to compile it once for x86 and then again for AArch64, or can you just build one jar file and then that has different shared object libraries for each of the architectures? How does that work? Does Java still fulfill the promise when you use AOT, that you get one package that you can run anywhere?
Okay, yeah, actually that's a very good point now that you mentioned it. The short version is no, and it's even worse than that. Actually, what's going on is the .so file contains some version information, which includes the particular architecture that you're running on, but also the JVM version number. So if you were to AOT something on Java 10, say, I think they had in 10, but anyway, well, better say 11. If you AOT something in 11 and then try to run it under 12, it's going to say, I can't load this. And that's even if it's AArch64 in both cases. So yes, you cannot AOT for x86 and expect to get it to work. But still, you're still pumping in the bytecode, so the bytecode portion is still portable. And as long as you aren't turning off the hotspot, then you're still going to be able to get improvement in performance. But no, you're not going to be able to run the AOT code even on the same core between Java 11 and 12, for instance. Even worse than that, says Stuart. Okay, let's hear it.
Well, when you're calling JOTC, you're passing JVM options, and those options have to match.
Yes, right. Good point. The options, but yeah.
But the code that's generated is very particular to the options that you're passing to it, so there's no expectation it would be portable over time or options or space or anything like that.
Yes, excellent point. Thank you. So yeah, AOT really has portability issues. Yeah, that's kind of what I get out of this whole thing, to be honest. Really, Hotspot is dang good. When you really get down to it, Hotspot is really good in terms of performance and portability. It's really, and that was the whole point of it, right? The whole point of it right from the start was to optimize portability, and it, as time went by, they just kept on getting better and better in terms of performance. So Hotspot is dang good. I'm really not all that optimistic about benefit from AOT, I have to admit. Hello, Stuart.
Hello. Did you look at OSR, non-stack replacement, in terms of the startup
No.
times?
Short version, no. What he's asking about is on-stack replacement is, okay, it really was mostly, as I understand, intended to make benchmarks look good, but arguably. But in any case, yeah. If you have a method that runs for a long period, long time, just never exits, but has a big loop that just keeps on running and running and running and running and running and running. Since what hotspot nominally, other than on-stack replacement, without on-stack replacement, all it optimizes is things that are called frequently. If you have a method that just keeps on running and running and running and running and running, it's not going to be called frequently, but it is going to be running a lot. So what on-stack replacement lets you do is still optimize that you can run in the interpreter and then flip over, so to speak, to a compiled version of it from there. No, I did not look into on-stack replacement, whether it was even being done at all or not. But again, I don't know if there's any option if you AOT something and then switch over on an on-stack as opposed to call basis. I'm guessing there's no way to do that on an AOT basis, but that's not what it's for. So, yeah. But yeah, good question. Anybody else? Oh, I'm glad I had time to do questions. It was quite a run to get this thing crunched down. Okay. Thank you.